Let's begin. Carboxylic acids, continued, slides 5 through 11. So making carboxylic acids, we've done already a bunch of times, right? So you can start from a primary alcohol, and if we use really harsh conditions like chromic acid, the Jones reagent, right, chromic acid, we saw that you couldn't stop the oxidation process. It went right through the aldehyde and continues all the way to the carboxylic acid. So that's probably one of the most prevalent ways that you see carboxylic acids formed is from a primary alcohol. We also saw oxidation at the benzyl position. Remember, the benzyl carbon, the carbon right off of a benzene ring, is a very special carbon where a lot of chemistry can happen because of the charges that can form and be stabilized at that position. Recall that a carboxylic acid can form at the benzyl position because charges can be stabilized at that position, whether it's a positive charge, or if you deprotonate, it's a negative charge, or even a radical. It's like the allylic position, but better, right? Because there are so many more resonance contributors that can stabilize that charge. As such, a lot of chemistry can happen at that position, including oxidation. And you do need some harsh conditions to blow off the other carbon that might be present and get all the way to just keeping the benzyl carbon present and oxidizing the heck out of it. But it's one of those flashcards I had you guys use because it was helpful when you were trying to derivatize a benzene ring. Lastly, we can look at a Grignard reaction. And one of the methods that we can use to get right immediately to the carboxylic acid is to react to Grignard with carbon dioxide. So what does that look like? What if I had methyl magnesium bromide? Remember that the methyl is negatively charged, and I introduce carbon dioxide. Now this reaction in reality is a little tougher to run because you actually have to have a tank of carbon dioxide and you have to have a solution with the Grignard in it, and you bubble the gas because CO2 is a gas, right? So you actually have to bubble it. It's not like you can go and weigh out on the balance some carbon dioxide. So it's not like the most dump and stir type reactions you can think of, but it is a 1,2 addition. In and up. So I'll write 1,2 addition here. That's typical of what we see with Grignards, right? 1,2 additions with a carbonyl. What does this look like? Well, I just had carbon 1. I added it to carbon 2. Carbon 1 is the CH3. Carbon 2 was from the carbon dioxide. And if you just kind of rewrite this, this is a carboxylic acid prior to workup, right? We're working under strongly negative carbon conditions, basic conditions, strong negative, right? Nucleophile, strong nucleophile / base. That means your basic conditions. Therefore, if you want to work this guy up, to get to the final product, you simply work it up under acidic conditions to neutralize everything and reprotonate your carboxylic acid. And that's it. That's how we know how to make carboxylic acids already, okay? There are a few other methods, and one of them I think is a very powerful one, and that's what we're going to talk about next. This is somewhat of a new reaction. I say somewhat because most of this mechanism, albeit long, is already covered in the ketone aldehyde chapter. If we start with a nitrile and we use acid-base chemistry, in this case acidic conditions under equilibrium, this is called hydrolysis. We saw this when we were doing imine and enamine chemistry. So I want to go over this mechanism with you because a nitrile is a really nifty way to transport the functionality of a carboxylic acid. Okay, and I'll show you what I mean after we go through the mechanism. So let's take a look. Here's your flashcard. We're going to do some acid-base chemistry in 1,2 additions. So this is very similar. You can think of the nitrile as kind of like an iminium system, right? An imine. So what I want you to recall as we go through this mechanism, I want you to recall from the aldehyde chapter that we had an imine was able to hydrolyze with water and acid and get us back to the ketone or aldehyde. Okay, so I want you to recall this reaction. Now, what happens with a nitrile? Well, let's say I have CH3, carbon, triple bond nitrogen. There's my nitrile. Under acid-water conditions, we're going to think about what happened with the imine under acid-water conditions, and we're going to draw some analogy to that. Okay, so with the acid, the nitrogen is going to protonate. And it's like we have an activated carbonyl, right? We have a heightened reactive electrophile because we're in acidic conditions, so we're making the electrophile positive. So our electrophile is positive. So we just need a weak nucleophile, right? Partially negative. That's going to be the water. So we just did the acid-base chemistry. And now we're going to do our in, up, down, out reaction conditions. Our water is going to be our weak nucleophile. And we're going to go in and up. And this is what I want you to see. Look at where we're at. It's not exactly an imine because we have an OH here. It's not like a ketone, right? It's got an OH, but notice that an imine under hydrolysis converts to a carbonyl. At this point, if you think of an imine hydrolyzing to a carbonyl at this point, because we just added an OH, we're going to end up with, you just stick the carbonyl right there, you're going to have a carboxylic acid. So I'm going to continue writing from here. And although it looks long, understand that this first step allowed one of those arms to be an OH. And now if we apply iminium hydrolysis mechanisms, then we're going to end up at a carbonyl here, giving us a carboxylic acid. So at this point, right, we're going to do a proton shift, because what are we driving on? Let's remember, we're driving water on because it's equilibrium. Of course, I could go backwards and pull the water off, but let's assume Le Chatelier's principle and I'm driving the water on. Okay, so we want to drive the water on and drive the nitrogen off because we're under equilibrium conditions. So we're going to H plus transfer or shift. So I did my in up. This is my in up. I did a proton shift. I'm now going to do my down out. Down out. And now we can just keep adding. We're driving our water on, right? So water is driving on. That means the nitrogen's driving off. Let's drive some more water on. Let's do another in up. in, up. Proton shift. Remember, that's going to pepper every reaction we do under acidic conditions. Shift or transfer, doesn't matter. We're driving the water on, we're driving the nitrogen off. So remember, the water stays on, the nitrogen is going bye-bye. Could we have made the nitrogen stay on and driven the water off? Of course, right? But we're assuming Le Chatelier's principle is driving us in the other direction. We drove the water on. We drove the NH3 off. And again, we're going to work it up under mildly basic conditions, just to get the pH back to the acidity of a carboxylic acid. And that's where we're at. Actually, I probably should change these arrows to more of a, once we got that. Okay, so I'd like you to go back and look at the imine chapter, or where we formed an imine and also hydrolyzed an imine, because if you look at this mechanism, it reflects the same protocols that we took to change an imine back to the carbonyl. The only added difference is that because we had 2 pi bonds, we could add 2 waters. In the imine, we only had 1 pi bond, so we only exchanged 1 oxygen, right? 1 water. But we get to the carboxylic acid because there are 2 pi bonds. So ultimately, we can go through it twice, putting the 2 oxygens back onto the system, okay? So very similar. I'd like you to sit down with some pen and paper. If you can really do the imine mechanism back to the carbonyl, you should be able to take a nitrile and convert it to the carboxylic acid. Okay, so now I've got this chart, and as we go along, we're going to start taking a look at how to go in between all of these types of systems. So in green is what I've highlighted as what we've covered already. A nitrile, as I just showed you, can go to the carboxylic acid. That's shown far right. We've also shown how a primary alcohol, down at the bottom, can be reacted under chromic acid conditions and give us a carboxylic acid as well. So these are the 2 main ones. Now we're going to take a look at all of these other systems and in between. I'll keep coming back to this chart so you can keep track of our progress. I also want to reiterate that from the mechanism motif paper that I gave you at the way beginning of the semester, what we're going to be concentrating on solely in this chapter is 1-2 additions, the in, up, down, out. And because if you think about where we came from, the ketone aldehyde chapter had us using the nucleophile to go in and up. And because R and Q at the beginning were both carbons and or hydrogens, we tended to go straight down and work it up and end at our alcohol, right? This is when the nucleophile is something like a Grignard or a hydride, right? We end up down at the first stop. At the moment now, in this chapter, Q is not a carbon or a hydrogen. So we're actually following the path definitively across here at the top, where Q is not carbon or hydrogen. So we're definitely going to come down and out, forming another carbonyl. And we have to consider doing the 1-2 addition again. So this is the regime we're going to be looking at, and it will be repetitive. So this is why this chapter happens to be a lot of people's favorites, because boy, they get really good at 1-2 additions. So the reactions of carboxylic acids. We're going to start with doing these 1,2 additions on carboxylic acids. And I think carboxylic acids are kind of the more difficult ones. And here's why. Let's look at the following carboxylic acid and a nucleophile. If you're adding a strong nucleophile, right, it's got a negative charge, what do you see as a potential problem? Well, nucleophiles we also call what? It's a nucleophile slash base. Which one or which function is easier to behave, right? A nucleophile attacks an atom that's not a hydrogen, while a base attacks a hydrogen. Both attack something partially positive. Who do you think's a little bit easier to access? Think about the functional group name, a carboxylic acid. We're considering attacking the carbon. If the nucleophile attacks the carbon, then we call it a nucleophile. If the negative species attacks the hydrogen, we call it a base. The problem is that these nucleophiles, or bases, can be the same species. They could be an OH minus, they could be a Grignard, right? So you've got to understand that our negative species is susceptible to attacking either the carbon or the proton because this is a carboxylic acid. They're both partially positive. And if you had a choice between the two, the hydrogen is way more electropositive than the carbon, and it is way less sterically hindered. So the base function will actually overtake the nucleophilic function. So the problem is, if you have a nucleophile that's strong, it's going to be a base and will attack the acidic proton. And that might not have been your intent. It's a distraction from maybe the nucleophilic behavior you were aiming for, right? So that's kind of one of the problems with the 1,2 addition on a carboxylic acid, is that you're adding a nucleophile slash base and you have a carboxylic acid. So there's going to be competition. How do we solve this problem? Well, we've got a couple tricks up our sleeve. And you guys actually already know what we did to solve this problem back in the alcohol chapter. Alcohols are not acidic, right? It's not super acidic. The pKa for an alcohol is roughly around, 16 to 19, thereabouts. While the pKa for a carboxylic acid, as we saw, is about 4 to 5. So even in the alcohol chapter, we were worried about deprotonating if we had strong nucleophiles. If they were strong enough, they were going to deprotonate our alcohol. Grignards are strong enough to deprotonate alcohols, right? We saw that in the homework, where sometimes if an alcohol was present and you were trying to make it act as a nucleophile, it was too busy deprotonating the alcohol. So what was our fix when we had an alcohol present if we wanted to make this a better leaving group without worrying about deprotonation? One of the fixes was to convert the alcohol into a better leaving group that didn't have a proton on it, namely a halogen. So we already know that good leaving groups are weakly basic and fairly stable molecules, or an anion when it leaves. Some examples of these good leaving groups are halogens, right? Cl minus, Br minus. These are very weakly basic. They're not strong bases. Why? Because they're greedy. They're very electronegative. They don't want to share because they're greedy. They don't want to do this. Again, the more electronegative you are, the more greedy you are, the less you want to share your lone pair. So they are weakly basic, and because they're atoms that are very electronegative, they're fairly stable as anions when they leave. So let's consider changing the OH of a carboxylic acid to a halogen. it will take that proton away from the game. We already know how to do this. The way that we changed OH into a halogen with alcohols was with PBr3 and SOCl2. Guess what? Here's the good news. It's going to be exactly the same as what we saw with an alcohol. So, as much as we tell you carboxylic acids are not alcohols, in this case, you can actually draw the analogy mechanistically to your alcohol. So, here's a review. If I have a carboxylic acid and I'm like, oh, yuck, I want to do 1,2 addition chemistry with it. I bought a whole lot of this carboxylic acid. Maybe I bought this very special one and it's rock solid as a carboxylic acid and it was cheap. So I wanted to use it. But I'm having problems because the nucleophile that I want to add keeps deprotonating and doing acid-base chemistry and distracting from the actual chemistry I really want. So I thought maybe I'll use PBr3 and convert this to an acid bromide. How do we do this? Well, we're going to do an SN2 reaction. Pretend that this is an alcohol. You don't hear me saying this very often. You do an SN2 reaction. There's my SN2. So far, it's just like the regular PBr3 reaction. And then you follow that with a 1,2 addition. The bromine that got kicked out is going, it can't do another SN2 because we've got a carbonyl here. So it's just going to do in and up. So here's our in and up, 1,2 addition. Down and out. Surprisingly, this unit is way more electrophilic, or a better leaving group, I should say. So we end irreversibly at the acid bromide. Remember, phosphorus oxygen bonds are really strong, and so this is your byproduct. But what I care about is my new acid bromide, which is now very reactive to 1,2 additions. Recall that there's kind of a bonus for running these reactions, because if you think about it, do you remember when we were talking about reactivity and we said that acid chlorides are way more reactive than, say, aldehydes, are more reactive than ketones, are more reactive than carboxylic acids? If your goal is to try and make a nucleophile attack 1,2 addition to your carboxylic acid, but you're having problems with competition and the reaction's not going well, you are actually solving a heck of a lot of problems by changing your carboxylic acid to an acid chloride. You're taking away the competition with the proton, and you're increasing the reactivity of your carbonyl. So it's a win-win. The only trouble is that making these, like, they're reactive. So you've got to use them immediately. Once you make it, you got to use it right away. You can't go to class and be like, I'm going to save it for, next week. No, you run this reaction, you make your acid bromide, and you use it immediately. All right, last slide for this part. We can also use SOCl2 and change the carboxylic acid to a chlorine. We can again draw our analogy to the alcohol chapter when we converted alcohols to chlorides. The nice thing about this, right, as opposed to the alcohol chapter, is we don't have to worry about inversion or retention, because the carbon in question is sp2 and it's flat and trigonal planar. So there's no stereochemistry. You just have to know that it converts the OH to a chlorine. So it's even nicer in this chapter, isn't it? All right, so our OH is going to do an SN2 with the sulfur. In in, out. We were able to do the SN2 and not in, up, down, out because sulfur has d orbitals, and so it's more likely to do an SN2. So we got our SN2 out of the way. And the chlorine is, again, just like the other one, most likely to grab the extra proton, acid-base chemistry, get things all sorted out. So we are here. Now, because we have the driving force of forming SO2 gas, that is going to be what irreversibly drives this reaction forward. We are going to actually have internal assistance by the oxygen. Take a look at this cascade. The carbonyl oxygen is doing a down out. To internally assist the leaving of SO2 gas. So we end up with SO2 gas. Right, that's going to bubble away. And the chlorine gets kicked off as well, and the chlorine is floating around. And now, because if you remember, chlorine's a terrible leaving group. I mean, a great leaving group, but a terrible nucleophile. So this is now a very activated carbonyl. It's a great electropositive electrophile. The chlorine is now enticed to react and do a 1-2 addition. So we kind of reversed our 1-2 addition. It's now a down, out, in, up. We assisted the leaving group, and then we had the in-up occur, giving us our R group back to a double bond carbonyl and the chlorine. SO2 gas is released, and we end up with our acid chloride. Remember, we actually used acid chlorides when we studied Friedel-Crafts acylation. And buying acid chlorides can sometimes be an expensive business, especially since they're so unstable. They're unstable because they're so reactive. Water, if you just have water around, moisture from the air, water will be the nucleophile and do in, up, down, out, and you'll end up back at your carboxylic acid. So these are very unstable compounds, and the best thing to do is to buy rock solid, less reactive carboxylic acids. Keep them on your shelf until you're ready to use them. Convert them to the highly reactive acid chloride, and then use them immediately once you form it. This is pretty much how Friedel-Crafts acylation works best. You make whatever acid chloride you want from the carboxylic acid, use your Lewis acid, aluminum trichloride salt, and your benzene to apply the Friedel-Crafts acylation. Now we know how to generate them.